morning, everyone. The whole chapter of wavelet transform. It will be covered from the book Conceptual Wavelet Transforms from D. Fugel. So most of the figures, what you will be seeing in this section of the chapter would be from D. Fugel. Okay. So we have already discussed that stationary signals are the signals which have a constant frequency all throughout the time period. Okay, so just like in any other joint time frequency analysis what do you call techniques, even in wavelet also these signals are regarded as stationary signals. Okay, secondly, if the signals they have a frequency they have frequency components which changes over time, they are regarded as non-stationary signals. Okay, now when we talk about wavelet, what is a wavelet? Okay, so wavelet is regarded as a waveform which is having a limited duration. Okay, which is having a limited duration that has an average value of 0. Okay, so you will find that a wavelet, it is a time restricted signal. Okay, so the first criteria for a wavelet is it is a time restricted signal, and the second is when we talk about this wavelet, the average value is 0. Of this of the wavelets are 0. Okay, so these conditions have to be met if we want to tell a signal that it is a wavelet signal. It is a wavelet. Okay. Now, what is the difference between a normal sinusoid and a wavelet? Okay, so if you look over here, it is a cosine wave. Okay, so it is basically an infinitely long sinusoid. Okay, it is an infinitely long sinusoid, and the important thing is that the frequency component associated over here are regarded as frequency. On the contrary, the wavelet, if you see, it is restricted within a period of time, and it is not actually a sinusoid, but it is somewhat periodic in nature within this restricted time period. And due to this reason, the frequency what the wavelet has, it is regarded as pseudo frequency. Okay, usually if you remember, we have previously discussed that in Fourier transform our basis signals are the sinusoids, which includes both sine wave and cosine waves, right? And we, for figuring out the frequency of a signal, we basically use these two sinusoids, that is the sine waves and cosine waves. And if you see, they have a constant amplitude and they are having a constant frequency. Okay. In the case of wavelet, also another important point with the sinusoids is that they are periodic in nature. In the case of wavelets, the signals, the wavelets, signals means the wavelets, they are periodic in nature just like the sinusoidal signals. Okay. However, they do not have a constant amplitude. The amplitude varies with time, and the signals are time restricted. Okay. So because of this phenomenon, we call that the frequency what we are associating with the wavelet, they are pseudo frequency. We are not calling it a frequency. Okay. Now, if you stretch this signal to the two ends, you will be getting a stretched or scaled sinusoid. Similarly, if you do the stretching of the wavelets like this, you get a stretched or scaled wavelets. Now, if you see the sinusoids, what has happened? What has happened to the frequency component? Initially, the frequency was higher over here of the cosine wave. When we have stretched, the frequency has decreased as compared to the original sinusoid. Okay. Similarly, over here, in the case of wavelet also, the pseudo frequency PF, it decreases when we stretch the wavelet. Okay. Now this is what it is written. The infinitely wrong sinusoid is stretched or scaled in wavelet terminology and is now a lower frequency. Okay. The dB20 wavelet is also stretched or scaled and its pseudo frequency or the average frequency is now lower. Okay. Now what we do when we analyze the high frequency components in the using the Fourier transform, we use a basis signal which is having a high frequency, and when we analyze low frequency components, we use a stretched version of the sinusoid to analyze the low frequency component. The same thing happens over here also. In the case of wavelet, the high frequency components of any given signal, they are analyzed using a high pseudo frequency containing wavelet or high pseudo frequency wavelet, and the low frequency components, they are used to analyze the low frequency component. Okay. So in our last class, we have also discussed over here that these wavelet, since they are time restricted in time restricted in their nature, so what happens is that they themselves, they act as a window. So they analyze only a particular portion of the signal. Okay, whether you are using a high pseudo frequency wavelet or a low pseudo frequency wavelet. Okay, so you are basically analyzing a small fraction of the signal while you are using the wavelet. Okay, so that means when you are analyzing a low frequency component, you are basically using a longer length or the scaled wavelet, and when you are using a high frequency component, you are using a what you call non-scaled or the relatively lesser scaled wavelets. Okay. Now, how the wavelet they work, it has been shown. So you have a mother wavelet. Okay. So for the wavelet transform, what you have the mother wavelet, you take it, then you shift the signal and do the correlation. Then what you do is that you stretch this mother wavelet, again do the analysis by shifting and doing the correlation, and then again you do the analysis by stretching and shifting. In this case, you have even scaled the what you call amplitude, scaled the wavelet in the amplitude fashion also. Okay, and then again you do the stretching and then shifting. Okay, so if you see, the constituent wavelets, they have different magnitudes, stretching, and the last is shifting. So so this was similar to the analysis of the signals using the Fourier transform. Over there we were having sinusoidal waves. So what we used to do, we used to have the sinusoids, do the convolution, okay, then what we had to do, we had to then stretch the signal, do the convolution, and in that way you needed to go, and also there was a phase shift over there. But in this case, in the case of wavelet, what we have, and also the magnitude of the sinusoids were also varied. We have seen that when we want to do the analysis using the Fourier transform, the basis signal, they were of different frequencies and different amplitudes, right? Similarly, in the case of wavelets also, you have different magnitudes, okay, just like in the Fourier transform. And then we have to do stretching. Stretching means you are varying the this thing, what do you call, you are varying the frequency component. In the case of wavelets, it's the CD frequency component, right? So these two are the similar things. And then shifting was not there in the Fourier transform, but it is here in the case of the wavelets. Why? Because if you have a long signal, as we discussed sometimes ago, we are having time limited wavelet component, right? So it will be basically analyzing a portion of the signal, but you want to analyze the whole of the signal, right? Hence this shifting is necessary in the case of wavelet. Okay. Then over here you have 2D time domain display, okay, 2D frequency domain display. These two, A and B, these are for the Fourier transform, okay. And lastly, in the case of wavelet, we have 3D wavelet display. If you see on the y-axis, we have scale, which is inverse of frequency, so which is basically the frequency axis, and then the time, it is also being broken down into small or bigger sections. So since inverse of frequency, we have put it as a, so inverse of frequency means the lower frequency will be on the top, right? So if you see over here, we are having larger window, and as we come towards the higher frequency, we have lower window for accurate analysis, okay. And the magnitude is indicated by the brightness. We have seen in the case of STFT also, STFT and also Wigner-Villay distribution, the pseudo Wigner-Villay distribution also, we had similar arrangement. We had x-axis as the time, y-axis as the frequency, and the amplitude, we had a color scale which is indicated by the which indicated the amplitude of the signal. So we had the 3D map, okay. Similarly over here also in the wavelet we will have a 3D map. So this is what I have told you previously also, just I made you understand. So suppose we are having a signal, pulse signal, which is basically the wavelet, okay. So in not the wavelet, this is the signal which is having a 20 Hertz component. Then we use a wavelet of dB20, which is of 40 Hertz, okay. So we do the correlation, then shift, again correlation, then shift. In this way we go, and then lastly we stretch the signal and then do the analysis in that way. Okay, the same way. So the wavelet transformation representation, it is regarded as scaleogram. Okay, so why scaleogram? Because we are scaling the frequency, or more precisely the pseudo frequency of the wavelet for the analysis of the signal. Due to this reason, the graphical representation of the frequency analysis of the wavelets, they are regarded as scaleogram. Okay, whereas the graphical representation of the STFT analysis, then Wigner-Villay distribution analysis, and all these things, they are regarded as this spectrogram. Spectrogram means spectral. Spectral comes from the meaning of the frequency. Okay, frequency and spectrum, they are sometimes quite interchangeably used. Okay, or the bandwidth, they are interchangeably used. So where you have this frequency component and the spectral components together, like in STFT, Wigner-Villay and all these things, they are regarded as spectrogram. Whereas in the wavelet, since we are talking about the scaling of the pseudo frequency, the graphical representation, it is regarded as scaleogram. Okay. The term dilation, it is also used to describe either stretching or shrinking the wavelet in time. Okay. So these are different wavelets. So first one is the Haar wavelet, which is the one of the most simplest form of the wavelet. Then we have the Shannon or Sync wavelet. We have Daubichel's 4 wavelet, Daubichel's 20 wavelet. Then we have Gaussian or spline wavelet. Okay, then we have biorthogonal wavelets, Mexican hat wavelet, and Queuflet wavelet. Okay, so these are some of the common and quite commonly used wavelets. Okay. Now comes the analysis portion. What happens over here? Okay. When we are doing the analysis, we have a signal component over here. Okay. Now this signal component, it has been broken down into approximate coefficient and detailed coefficient. Okay. Now when you do this, so you are basically applying a low pass filter, you are applying a high pass filter. Okay. Then what happens when you are reconstructing it? You have another L dash filter which corresponds to the L filter, and you have another H dash filter which corresponds to the H filter. So these are called, these H dash and L dash filters, they are called reconstruction filter, and L and H, they are regarded as the decomposition filters. Now once you do this, after the reconstruction filter, both the signal components, they are added and you get the S dash component. Okay. If you have not done any manipulation in between, then your S dash is equal to S dash. Okay. And this lower one, it is called A1 and D1 accordingly. Okay. Now I have a question. You have applied a low pass filter and a high pass filter over here. Now say the signal component S, it is having a length of 200 points What would be the size after this filtering? Or say over here at D1, what would be the size? Here also, let's say what would be the size? A, B, and this signal C. And if you want, you can also tell this D. So anyone who can tell me? What would be the size of the signal? Oh, sorry. What would be the size of the signals at A, B, say C and D? Okay. So we are assuming that the signal, original signal, it is having a size of 200 points.
Say AB equal to 100 and BC equal C equal to 100, D will be 200.
How many of you agree? How many of you agree and how many of you do not agree? क्या बासु जी?
Yes, sir.
हाँ. Do you agree?
Yes, sir.
You agree. Who else are there? The simple thing is, say for example, we have a signal xt, say t, and amplitude. Okay. When you do the Fourier transform, or in this case, say fast Fourier transform or the DFT, then and it would be, then we have omega amplitude. Okay. Like this. So from here you have analyzed that it is having a 10 Hz signal, say for example. Then you have 20 Hz signal. Then you have 30 Hz and so on, say for example. Okay. And you want to pick up 20 Hz signal. So you apply a band pass filter over here. Okay. Again you are getting this thing. What should be the length of 1 and 2? Will that be halved? Yes, Nilanjan Babu. When you
Sir, it depends upon.
say in the case of analog filter also, you have a signal as, you have implemented a high pass filter. You have got signal S dash. So the signal length of S and S dash, they are different.
No, sir, length remains same. Length will remain same.
Length will remain same. So why over here it will become half?
No, sir, it won't become half then.
So it won't become half. Then it is 200 and 200.
200. At all points, it will be 200.
All points. But you said here it was doubling. So as per that analogy, it should have been 400. Then why it should not be 400? Yes, Basuji. Now Niranjan
Yes,
doctor
sir.
has changed his stance. 100 से 200 हो गया अभी बी एंड सी में एंड ए में भी वो बोल रहा है डी में भी 200 होगा बट पहले वो ही सेड that it would be the double of what it would have been in B and C. Now he is keeping same. Now why it should be same? Any idea? Anyone?
No, sir.
That means your basics are not clear. You have not studied this signals and systems part. That's why I tell you go through the basics. Even though you have most of you have gone through this basics of signals and systems, I still cover it due to this reason. Okay. So what happens? Suppose you are having x0, x1, x2. This is time. So addition is through point by point addition. Are you getting my point?
Yes, sir.
So this one is having 200 points. This one is having 200 points. So if you add these two, how many point signal you will be getting? You are doing point by point addition. Number of
200
points
only.
in time it would not
200,
change,
sir.
right? So when you are doing the addition, your amplitude is changing.
Yes, sir.
Time point does not change. Time period remains same. Even in FFT, whatever you do, the number of points, if you remember our this DFT or the FFT, this thing, because everywhere we implement FFT using the computer. So what was the input? Your input and output, this thing, what do you call? Input and output length, both were same. How you are telling those are different? Right? When you applied the filter also, when we went for this high pass filtering and the low pass filtering in the FFT domain, were the length different? Whatever was the length of the input, that was the length of the output too. Okay.
Yes, sir.
So when you pass the signal through high pass filter, it would have same length. This reconstruction filter H dash, same length. Everywhere it would be having a same length. Okay. Now if you combine this H and H dash filter, because they are in series. Now this series, it is called high pass half band filter and low pass half band filter. Okay. Now this was the case about the length, whatever I was telling. This was the case for the undecimated discrete wavelet transform. Undecimated discrete wavelet transform. Okay. Undecimated means the signal is not reduced in length. Okay. Now there is another kind of wavelet transform which is called decimated discrete wavelet transform. Okay, so in that, what you do, you after filtering, you reduce the signal length by 2. Okay, so when you are doing this, so what would happen?
So the
Here
length will be half.
the length would be half. Okay, ultimately, when you try to reconstruct the signal, sorry, it will be again up regulated and the signal will be S dash, such that you have S and S dash which have same length. Okay, so this is downsampling, and then this upper arrow, this is upsampling. So in many cases, we will see that we do not do this reconstruction, but in many cases we also do it. So depending upon what we want to do. Okay, so suppose we want to go to a specific frequency band, then we do not reconstruct the thing. So we only take those specific bands for the analysis. Okay, in the undecimated one, so what we do basically is that suppose we are having S, we apply high pass filter, we get one component, we do get L, we get another component. Suppose this is having, the signal is having a maximum frequency of 100 Hz. So the high pass filter, it would be having a filter component of say 50 to 100, and the lower one will be having 0 to 50. Okay. Now again, if I go for the second level of decomposition, this will be broken down into 25 to 50, and the lower one will be broken down into 0 to 25. So see, we are slowly decomposing the low frequency components over here. Okay. Again, if you go for the third level of decomposition, we would go for 12.5 to 25 and 0 to 12.5. I am talking about the frequencies. These are frequencies. Okay. FM equals to 100. So we are applying low pass filter and high pass filter. Over here also there will be a low pass filter, a high pass filter. Here also there will be a low pass filter, a high pass filter. Are you getting my point? So at each level we are applying a low pass filter and a high pass filter. So we are just breaking those down. Okay. So what we want to do, suppose at the end, what are the components we will be getting? We will be getting this one. Okay. So this is D1. This is D2. Say for example, I am not naming it in this thing. So this is D3 and this is A3. Here we have, this is A1, this is A2. Okay. A1 is the approximate coefficient of level 1, A1 D1, approximate coefficient 2, and D2 approximate coefficient 3 and D3. So at last what we are getting? We are not getting A1 and A2. The final results, what we are getting D1, D2, D3 and A3. Okay. Now if you combine these frequency components, if you see 0 to 12.5, 12.5 to 25, 25 to 50, 50 to 100. So if you combine all these frequency components again, then what do you get? You get a S- signal which is having frequency component 0 to 100, right? All the frequency components are there. So that happens if you go for the reconstruction of the signal after doing some analysis. Okay, but in many cases, say for example, if you want to go for classification, you want to narrow down to a particular frequency component. So suppose you get this 50 to 100, you will be getting one frequency, one signal. So suppose the signal length is 200. All of these they will be having 200 length, right? L equals to 200, L equals to 200. All of them they will be having. So you can find out the features of these signals. Okay, you can find out the features of this signal. So suppose from one signal you get, say from here you have made a program and you get 9 features. Okay, now from each of these D1, D2, D3, A3, you can get 9 features each from everything, from each of these things. But the additional advantage over here is that you are getting the features from a particular frequency band. In the first case, you are getting it from the whole 0 to 100 hertz signal. Okay, now you are getting frequency specific features, frequency band specific, not frequency specific, frequency band specific features. Okay, now again, suppose you have a signal, or you have a signal where you know that there is a 16 hertz noise. Say for example, there is a 16 hertz noise. So you are having it in D3. So while the reconstruction of the filter, what you do go for D1 plus D2 plus A3. For the total reconstruction, you need, in this case, for getting S dash, D1 plus D2 plus D3 plus A3. You need all the components. But if you want to do the filtering operation using the wavelet, then say if this is double dash, then what you have to do, you have to go for D1 plus D2 plus A3. If you apply these, if you add these filter coefficients or the signal components, then you will be having a frequency component which will be removed. Now if you see, it is a long range. Okay, now if you want to go to a more specific or to a very narrow range, you have to go for the higher level of decomposition. Over here we have got only level 1, level 2 decomposition, right? So if you want to go to a more specific this thing, if you see, you cannot go it over here in this case, in this wavelet transform, because in all of this we cannot decompose in wavelet transform, normal wavelet transform, we cannot decompose the D3. Okay, so we cannot do the analysis, we cannot go for further decomposition of the signal. But if it would have been say 9 hertz component, this A3 could have been further decomposed. Say you would have got 6.25 to 12.5 and 0 to 6.25. Okay, so now this 9 hertz, it is there in D4 and this is A4. So this 9 hertz component, it is now getting into this thing. So you see, you have narrowed the band. Okay, So in this way, you can go for the reduction in the bandwidth for eliminating a specific frequency. As you go on increasing the level, you will be able to reduce the bandwidth of the different signal components. Okay. So whatever I have told, it's written over here. So we do decomposition, okay, and it is done into two parts using high pass and a low pass filter. Each of the two parts themselves can be decomposed further, split into more parts using more filters. So reconstruction means using filters to combine the parts, and perfect reconstruction means that the signal at the end is same as the original signal. Okay. So the approximation in wavelets is the smooth signal after all the low pass filtering. Okay. Details are the residual noise after the high pass filtering. CA1 designates the approximate coefficients and CD1 designates the details coefficients. These coefficients can be broken down into further coefficients in higher level systems. Half band filters split the frequency into low pass and a high pass half, usually with some overlap. All four filters are regarded as wavelet filters. Okay. So if your sampling frequency it is 200 Hertz, that means while you will be doing the frequency decomposition using the wavelet decomposition using the wavelet transform, you will be getting up to 100, because in that case FM is equal to 100. So this signal, the signal which is having say 0 to 100, it is broken down into 0 to 50 and 50 to 100, right? These are hertz. If the filters are non-idealistic in nature, there may be some overlap. Okay. Now the approximate coefficient what I have showed you, that can again be broken down. See, the original one, it has been named as D1, then you have D2. So A1 is broken down into D2 and A2. Okay, and further if you go for the level 3 decomposition, this A2 will be again decomposed into A3 and D3. Okay, and if you add the bandwidth of all of this, then you get the original signal. Now this is what it is told. I have already told you. High pass filter, low pass filter, level 1 decomposition. From again here, this one and this one is being broken down. A1 is broken down into D2 and A2, and then you again reconstruct the filter. Suppose if there is any noise in CD2, so what you do during this reconstruction phase, you do not use this part for the reconstruction. So if you do not use this part, you make it blank, then there will be a combination of A1 and D1. Now this A1, it is basically composed of D2 and A2, but we are not using the D2 component. So if you do not use the reconstruction filter of D2, you will get finally over here D1 plus A2. Okay, and D2 will be eliminated. Are you getting my point? However, as you have seen in wavelet transform, what we have found, this 12.5 to 25, if there was a frequency component of say 16 Hertz, we are not able to decompose it. Okay, so that was one of the major problem, and the researchers found that if we can decompose the detailed coefficient also, then we can go for better analysis. So what they did is that, suppose you are having this signal 0 to 100, they went for the decomposition 50 to 100, 0 to 50, right? Same what we have done in the wavelet transform, but in the next level, the detail coefficient was also broken. Say for example, this would be 75 to 100 and 50 to 75. Okay, and over here we would have 25 to 50 and 0 to 25. Okay, so if you see if you add up all this bandwidth, 0 to 25, 25 to 50, 50 to 75, 75 to 100. So again, if you go for the reconstruction, you get, say this S, this is S dash, so S is equal to S dash, there is a perfect reconstruction. Now if you want that there are certain components, say 60 Hz components you want to eliminate, then you do not use this. So this is A1, A2, sorry, D2. In this case, naming will be A1, A2, A1, D2. This one. Over here it will be D2A1. So whatever is there, D2A1, and this one will be D1A1. Sorry, D1A1 and sorry, no, this is a D1. Yeah, and D1, D2. Okay. Now getting my point, how the naming goes. Now again, if you try to break this down, you will be getting A1, A2, A3, and the other part you will be getting A1, A1, A2, D3. Are you getting my point? How we name it?
Yes,
so
sir.
if you do this kind of decomposition, then it is regarded as wavelet packet decomposition. Again, you can go for the similar kind of reconstruction also. So if you see, it is the signal, and it can be again renamed as, say, 0 and 1, named as 0 and 1. So 0, 1, then 0, 0, 0, 1, then 1, 0, 1, 1. Again, this breaks down to 0, 0. It comes from here, and again 0, 0, 0, 1. Then this comes as 0, 1, 0, 0, 1, 1. So in this way, we go for this thing. Now over here, we can go, as we go on increasing the level of decomposition, we can go to much narrower bandwidth. Okay, we can go and we can target a specific frequency component. Are you getting my point? So in this way, we can do the wavelet packet decomposition. Okay. So any questions?
No, sir.
If you guys have no questions, then we will just stop